Okay, so let me start. What about the subject of the lecture? No, first of all, thank you very much for sure. And about my talk and lecture, I'm talking about vertex operator algebras. And this vertex operator algebra, what I'm talking about, no, so surely this is the old object. And now they're interested to this again. No, it is something interested returning and returning. And what I have in mind, it is the, the following story. Now, vertex operator algebra, what I'm talking about, it is some algebraic object. It is usually contained Virasoro subalgebra. Yes, and it if we have vertex operator algebra, it means that we have in a mind some conformal field theory behind it. And two-dimensional conformal field theory, it is an object which is deeply connected with the vertex operator algebra. And the recent story, what I have in mind, and maybe in the end of my talk, I am explain something, that this is some kind of many conjectures that if we have manifold, then no, it can be from topology or from algebraic geometry. From algebraic geometry, corresponding object, usually calling the symplectic duality. This is a story that if we have symplectic manifold, then it is some kind of conjecture, sometimes some way to do it. We can construct the dual symplectic manifold, and it is very interesting and a deep story. And so there are many machineries how it is going on, but it is going on through conformal series. So it means that for symplectic manifold, we can correspond to some vertex operator algebra. And same story we can do for the dual one. And this is actually correspondence between two corresponding conformal field series. And so we can construct it, and using some property of this vertex operator algebra, we can construct dual things. And no, people working about this, and I can say several names. It may be Gayotta, Arakawa, Finkelberg, and with co-authors like Braverman, Kajima, and so on. So this is the interesting story. But I start not with this, but just maybe I recall something about vertex operator algebra and the duality in the vertex operator algebra world. Such kind of duality appear, and from mathematical point of view, it connected with Lenglen's duality. And all this story, in some sense, is very, very deeply related with geometric Lenglen's. But let me start first with the old all things are the following. So if we have some kind of semi-simple Lie algebra, this will be corresponding current algebra. And with the current algebra, it has level, which will be K. Yes, and Lie algebra G define the universal enveloping of G hat, which is can be considered as vertex operator algebra. So this is usually the main building block for all vertex operator algebra which we can study, and main tools, because vertex operator algebra usually is rather abstract things, but if we want to say something, it is good to have some explicit construction. Oh, can you see or not? Something happened with my screen.
You have zoomed out. You should zoom in.
Oh, what is happening? Maybe I have to go out.
You can try it one more time. And I would ask everybody in the audience remove their pointers from the blackboard.
Okay, okay.
So press this.
No, now I return back. Yes, so can you see now?
Yeah, we can see it. It's back to normal, yeah. We can suppress it. No.
Yes,
for the moment, you continue.
So excuse me. So the main construction, so I start with such kind of algebra, and then I can produce the new one, making what is usually calling the quantum Hamiltonian reduction. So reduction, it means that most popular quantum Hamiltonian reduction, this is what is calling Drinfeld-Sokolov reduction, and it is going on by the following way. In G, we have maximal nilpotent subalgebra, then we fix the character. So it is hat, it means that I am talking about the current, and we have character of n hat to C. Yes, and after that, I can make up a Hamiltonian reduction. Maybe it is not reasonable to recall what does it mean, but Hamiltonian reduction, this is the main construction which we have algebra A, subalgebra B, and maybe character, and we can cook out the new algebra H AB, which is a reduction with respect to B. So in the usual story, we are considering subalgebra in A, which are acting on invariant with respect to B. But it is a Hamiltonian reduction. It means that we kill some subalgebra and make up a smaller algebra, which is like this. And some people call it the geeky algebra because it is usual geeky if A is group algebra of J-len over finite field and B is nilpotent subgroup. Anyway, we can do this, and let me just recall that if we take SG SL2 hat, and if we have n hat, then the result of such reduction, we start with SL2 hat, and going to the Rasora algebra, Yes, and maybe it is one of the best way. No, this is some correspondence, but we have in mind also some functor. So if we have representation of SL2 hat, we can make up representation of Virasor. And the one of standard notation, if I have G hat and of some level K, and make up a reduction what I'm talking about, then I get the object which is standard calling W algebra corresponding to G. So by this way, we get some collection of W algebras and also conformal field theory and so on. Yes, and this is most popular vertex operator algebra which exists. Now, what Lagrangians first appear by the following way. We can take G and dual to G. It is Lagrangian's dual algebra. We can take this, and they, after that, we can make up this Hamiltonian reduction for this and for this. And we get two double algebras, which is first for G and second for G check. Yes, and here we have K, and here we have K prime, and such kind of double algebra. So we have two families of double algebra, which depending in this parameter K, and one of the main statements about this, that that's such kind of double algebra, I mean this one and this one, these two families are isomorphic. After some replacing of parameters K to K prime. Now, what kind of how to replace, but at least what no, this is fact is important because these two algebras surely are different, and they have a different representation theory, but the result of reduction is just the same. Yes, and no, I can make some maybe later some comment about this, but one possible to use this fact, using of this fact is following, that we have, if we have W algebra KG, yes, and such kind of W algebra depending in K, and it has two, let us call it classical limit. Classical limit, it means the following. So we have just a family of the algebra. And if, no, it is vertex operator algebra, but we can understand it as thinking by the same way as about associative algebra, it is possible. First classical level, if it is possible to send K to infinity. And in this case, it means that classical, word classical, I mean that in such limit, algebra become commutative. So, no, first of all, it is the question how to make up this definition. I cannot explain the details, but it is possible. And this algebra is commutative, and if we move a little bit, infinity plus epsilon, then it is a sort of quantization. So we have commutative algebra with Poisson structure, which appear by this way, and all story can be understood as the quantization of this algebra, and this W infinity appear usually as a space of functions on some Poisson manifold, and this Poisson manifold usually calling operas, and they appear rather often in a different part of our science. And this Poisson manifold, they are always some kind of differential operator with Poisson structures. So for SL2, for example, this manifold is differential operator with a standard Poisson structure which appear in integrable system business. Yes, and other classical limit, it is going on to, for Kac Moody, we have so-called critical level. So critical level, this is situation which appear for universal enveloping of G hat, and it is happening in many, what I'm talking, G can be Lie algebra or superalgebra if you like, but it is some special value of K, where K critical, where this algebra has what is calling the big center. No, the idea is roughly the following, that if we have algebra G and we have universal enveloping of G, so it has some center. And because G hat is affinization, so it is current of from the circle to G, then in universal enveloping, we also expect affinization of these centers. Now, center for UG always function on sums. And we expect that after affinization, it will be center, which are functions on current to the spectrum of Z. So, so this is a natural expectation. As it is not true. But if K is critical, then we have such center, and such situation is true, at least in some sense, not maybe precisely, but it is true. And for some critical level, it is a big center. And it is one thing. Other things that the limit of my W algebra of G hat, when K goes to critical level, it is this limit, let us put here Kac critical, this limit is centered on a critical level. So what is the situation? We have a family of W algebra depending in parameter K, 2 points. And here we have one classical level. Here we have second classical level. And the whole algebra can be understood as quantization from this side or from this side. And this is operas, so they are connections, and here the center. Duality, it means that we have this is family of G, And this is family of W G check. Yes, and I said that these two families are isomorphic, but isomorphism is some kind of changing of key. And two classical limits for this family and for this family, they interchange. So this is going here and this is going here. This is, in principle, we expect that this is generic phenomena, but it is using by the following way. If I want to say something about center of G hat on a critical level, I describe it in terms of dual group and usual classical limit for that. So it is orders. So from this, we can derive that the center on the critical level is the space of function of some connection of orders, actually, like some connection type things related with G hat. So this is a phenomenon which extensively using in geometric link length program in the integrable system and so on. But let me ask the question, maybe it is for now rather technical, but interesting nevertheless. All this, what I'm saying, is working if G is semi-simple Lie algebra. But suppose that G is superalgebra, for example, if it is JLNM or any other. No, it is maybe one of the main example. No, by example, I mean the following, that this is archetype of some kind of things. So we have a family of algebras depending in K with two, maybe sometimes more quasi-classical limit, and for different algebra they coincide. But for at least naively for superalgebra, this scheme is not working because of the following. So first, if I have universal enveloping of G, L, and M, so it is also critical level for any superalgebra, which maybe only some exceptional case, which I do not discussing now, but usually it is also critical level, and this is the center on the critical level, and we want to describe what is this. And no, it is a really interesting story because no description of a center for GLMN in principle is known for a long time, and center of GLMN, this is the following object. We have pseudo-differential operators like dn minus m plus dn minus m plus so on, and pseudo-differential, it is -1, then n minus m minus 2 plus so on. And center is the functions, so till infinity, so negative powers. No, this power also can be negative if you like, but they become more and more negative with some coefficients. If some such differential operator, it is some condition that this differential operator can be written as d1 times d2 inverse. d1 is a differential operator of order n. d2 is differential operator of order m. So this is pseudo differential operator of order minus m. Yes, and if we can write differential operators by this way, and it is some subset, submanifold, infinite dimension over this space of differential operators. And there are some kind of, this is theorem, I think it exists for a long time, that I don't know, maybe it is not written, but definitely many people know it. That center on a critical level just a function of such object. Yes, and similar but more complicated answer is known for other superalgebra, for example, for OSP or so on. But the question, what I want to discuss, and the answer still is not known, can we understand this phenomena from this Lagrange point of view? Can we apply these nice arguments which I presented before to say something about center on a critical level? And it is not fully known, but what is known, I'll try to explain. Now, first of all, if I have a universal enveloping of G hat, then we can make up the Hamiltonian reduction, quantum Hamiltonian reduction, and produce W-algebra depending in G, even in a case when G is superalgebra. There are some subtlety how to do it, but it is possible. So we have a family of algebra depending in K, and so this is more or less the same story, up to some details which I can skip now. So this is infinity, and in infinity it is something which can be described in terms of connections. Now, it is some kind of super connections and blah, 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 but it is possible to say. This is a critical level where it is center, and center we expect no, no, in fact, what we want to find the dual family where it is interchange of two quasi-classical points, and if we achieve, we are happy. And what I want to say, it is possible to do even by several ways, but not very satisfactory way. So first, let us, I'm talking only about JLN case, and so let us take JLN algebra of level K, and let us consider JLN minus one algebra here, also surely level K. And in this case, it is some conception of Coset algebra. Meaning of Coset vertex algebra from algebraic point of view, it is no, it is some kind of good definition, but naively it is following. If we are talking not about Coset algebra, but about usual one, we have like this. And we can ask about commutant. so the subalgebra here A, which commute with this. It is some kind of approximate what I want, but at least in this case, such kind of algebra, this is commutant of universal enveloping of GLN minus 1. Now without hat. Now it is what is P in Gelfand-Zeitlin business. So if we have a representation of GLN finite dimensional or not, if we restrict it to subalgebra, then, and if we want to decompose that, surely this algebra is in charge of such kind of decomposition. Gelfand-Zeitlin's story is based on analyzing of this algebra. And if we are talking about the affinization, so the question is just the same, but we put heads here, and we wanted to ask what is this. No, this is surely, no, this example is known, and maybe in my talk I can have no time to say something really new, but there are many open questions here. Anyway, in this case, such kind of commutant is, no, here this algebra is commutative. Here the commutant, first of all, it is vertex operator algebra. It is not commutative, and it is also depending in parameter k. But the remarkable and surprising effect that this Coset vertex operator algebra is isomorphic to W-algebra for superalgebra for JL n minus 1. There are some reasons, in principle, why superalgebra can appear, but we, in some sense, we do not have something super here. I'm talking about the usual algebra taking Coset and want just to. Anyway, it is such kind of algebra, and so this story about this Coset, if you have this, you need to have in mind what now calling of Guyot conjecture. No, Guyot has many conjectures, but now it is some of his recent conjecture. But this conjecture is geometric, and this is what Finkelberg and other guys, Nikajim and Braverman and many others are studying, and this is the question about Grassmannian, affine Grassmannian for JLN. And conjecture saying that in such manifold, no, Grassmannian for JLN, it is affine Grassmannian, it is a Grassmannian for algebra for JLN hat, some kind of Flag manifold, and meaning of conjecture that if we consider the constructive shifts which equivalent with respect to JLN minus 1 over, or it is this. Then this by this way we can, by some work, recover the category of representation, even if you are lucky, of quantum JL and minus 1. So this is the conjecture, and maybe theorem now, not conjecture, but anyway, from the point of view of vertex operator algebra, this is the fact which I'm talking about, and maybe Gayota based on this fact. This I do not know precisely, but I think it is. Anyway, but why, again, why such kind of isomorphism is true? No, again, it is still mystery, and any explanation, it is nice. But anyway, what we have, if we believe that it is correct, we have J ln, we have J ln minus 1 hat, and taking the reduction, we get family of vertex operator algebra depending of level here, and this is it. If you have such kind of construction, surely you also can ask about classical limit. K can go to infinity for J ln, or K can go to a critical level, which is for J ln is minus n, and they have in both cases some kind of limits, and phenomena which was in this Lagrange story repeated in the following sense. Again, we have two different kind of construction. One construction is well, W-algebra for JL and n minus 1. No, it is also reduction by definition, and we get some family of algebras. Here we have different reduction. We have JLN hat and making reduction over JLN minus 1. And again, we have a family of algebra with two classical limit. And the story is that this Lagrange phenomenon is true. So it is some changing of variables when such algebras are isomorphic, and two classical limit interchange. So again, naively, it means that I take superalgebra JL n minus 1, and from this point of view, the dual thinks it is something like JLN times JLN minus 1. No, it is not precisely correct. So here it is something. Here we have to make up a little bit more drop. But in some sense, such things is true. So now let me present one more example of a similar kind. By similar kind, that I want to make up some other reduction and get W algebra, which I can identify. The simplest interesting example is following. So let us take this will be trillion, yes, and this is nilpotent. And the people are studying usually the following question, that this is a question which it can be appear as a name as finite double algebra if you're talking about JLN, or generic W algebra if you're talking about current algebra. Anyway, the question is following. We have G, we have nilpotent subalgebra, maximal nilpotent, and we have some subalgebra which is N sub. Some smaller nilpotent subalgebra here.
Maybe Yeah, maybe a quick precision, just 2 lines above. When you talk about this duality, which mean you can rewrite, am I correct? The W-algebra of this GL superalgebra in terms of the Coset of affine GL. Is that true?
Yes, yes.
Yeah, right. But now I'm just
No,
wondering.
again, I realize this algebra by different way, like this.
Yeah, right. But this also holds at the points like at the critical level and the classical limit.
No, this no, it is the same story. So for these two families, meaning of parameter k are different, and it is some change of variable, and two limits interchange. So
Okay.
this is the same phenomena which happened for G and G Lagrange dual, just the same things.
Yeah, that I see. So,
But anyway, but different way. Anyway, now let me. How much time I have?
Maybe 20 minutes more.
Okay, fine.
Yeah, thanks.
So one more. So I am talking about what? That we have nilpotent algebra. We have some subalgebra. Yes, and maybe some representation or character of subalgebra to see, and then I can ask about reduction of, no, even in finite dimensional case, I can take this. I can take universal enveloping of subalgebra. No, I can take also character or not, but it give after reduction, I give something. Yes, and the popular things that which it is, if we have some nilpotent class of nilpotent elements, maybe A from N, then I do not want to formulate it, but such kind of story, each element determine the subalgebra, determine the character, and we can make our reduction. And people study a lot what we get and describe it in terms of some Youngians and so on. But this is some special case. In principle, we can take any subalgebra here and we can make up reduction and we always get something. And the question, what is this? It is nice open question just to try to characterize this object in some generality. But my example is following. I want to take n sub just commutant of n. It is just this. Yes, and what I want to do, I want to take universal enveloping of JLN hat, and here it will be n hat, and no, usually I use character. In this case, I do not want. Character is 0. So it means it is standard reduction, just algebra and such kind of subalgebra. And so notation is bad. Here it is n, and this is maximal nilpotent. Yes, and so, no, we get some algebra. At least in this case, the answer can be described. And again, up to some details, such kind of Coset, it is some simple factor, which is just Heisenberg, which I want to forget now. And remaining factor is still our W algebra of JL and minus 1. So it is looking that no, in some sense, it is just a phenomena which I describe talking now, that you can take JLN hat and then you can make up two different reductions. And one reduction I mentioned before, it was Coset with respect to JLN minus one hat. Second, Hamiltonian reduction, which this is here. Yes, and no, in fact, I'm talking that we get the same things, and let me just present one more example that but in a similar kind. So it is still JLN like this. And before I take just reduction with respect to this. And I'm just saying that, if you make reduction naively, it means that you have this, you kill opposite side, and what remaining, something living here. And because of some reason, this is a W algebra for JL, say, n minus 1. Yes, but you can do a little bit more. So you can consider bigger algebra, for example, like this. And it is just, you see, it is just commutant of n, but you add one root here. And for this bigger algebra, it is now also, it is now n. Maybe I put 1 here because I add this root, and a character sent this generator E non-trivial here. Yes, so it is some kind of character, and I can make up the reduction with respect to this. And by this way, we can get WJL n minus 2. Yes, and if times some Heisenberg. If you make this, then it will be n minus 3 here, and so on. So conclusion, or just what I claim, that you can get W algebra of JL and M. No, in general, for any NM, just modifying this construction by this way or that way, but we can get it as the appropriate reduction of JLN hat over some subalgebra. Yes, and okay, so no, I can ask the question, and I actually do not know the answer. Maybe no, question is so for JLN, in principle, I made some calculation, and it is possible to check, to prove, to be more or less sure that this is correct. But you can consider some other example. You can take ON, for example, and hat. It is orthogonal algebra. Here you have maximal nilpotent, and you can play the similar game. And the question, what you get. No, if you take O n reduction with respect to character of maximal nilpotent, then you get W algebra which associated with orthogonal algebra. If the experience is now that if you consider smaller than the whole algebra, then the answer has to, in some sense at least, has to be described using language of superalgebras. For example, what is really known that if you take On hat and taking Coset of On minus 1 hat, like this, it is not this business, but I make Coset with respect to subalgebra, but in fact it is similar. This is the answer depending on a parity of n, but for example, if n is even, then it will be OSP to n and n minus 1 W algebra. So just making reduction or with respect to On minus 1, as a result, you get the reduction OSP n minus 1. Yes, and I want to stop about these examples, but maybe only one small comment, which is also natural. So, for example, if you take JLN, for example, over JLN minus 2, Coset, so what you get? And the answer is that it will be vertex algebra, which is a generalized W-algebras, and it has name. It is usually calling the toroidal Yangian, and I have no time to explain what it is, but I want to say that all the statements which I presented have the analog in this situation. Maybe I have a few minutes, and I only want to say how in principle, duality can be applied for the symplectic duality business. Yes, for that, no, only very short words. Symplectic duality business in standard presentation, it is general things, but people like Benzvi and other, they are studying the following situation. Suppose M is a symplectic manifold, and suppose also that Lie algebra G, Lie algebra, or in examples which are not studied, superalgebra is acting in M. Yes, and in this case, no, it isn't situation is completely not general. So it is just small. M has to be rather small, but from philosophical point of view, it can be any in principle. Yes, and in dual world, we are thinking that it has to be dual manifold where the dual group is acting. Yes, and strategy is the following, that we have M, and one things we want to construct. No, if it is a symplectic manifold, just symplectic manifold, then we have, no, usually in standard example, M is affine, and it can be quantized, and we have function on M, and then we can quantize and get some associative algebra. Yes, and we can consider affinization, something like this. And on a place, no, it is some kind of Poisson-symplectic structure here, and we can manage to quantize it, and it gives us, if we manage it is, in examples it is possible. In general, there are some theorems, but they are not very useful. Anyway, we can construct vertex separator algebra, or want to construct vertex separator algebra, which is corresponding to this. Construct, and after that study representation of this algebra, and if we can construct, if we have vertex separator algebra, then representation, because it is vertex separator algebra, then category of representation have the tensor structure. And how such kind of idea is working, that suppose we know that G is acting on M, it means that G hat can be embedded to this vertex separator algebra, and in examples it is like this. Then, because it is vertex separator algebra, it has vacuum representation, which is also representation of G hat. Then, how we proceed after that? So in vertex separator algebra world is the following. So this is a representation of G hat, and because it is vertex separator algebra, so it means that this is representation of with the product, which is something like that. Actually, this is operator product. But also we know that representation of category of representation of G hat is equivalent in some cases. So suppose that level K is negative. Negative, it means that it is less than this integer and less than critical level. It is not necessary, but suppose for a moment, K can be even not integer, but let us, we know that in this case, following Kazhdan-Lustig theorem, that appropriate representation category is equivalent to representation of Lustig quantum group, which is something like UQ of G, but in a root of unity. And in a root of unity, and And this group is what? It has some subgroup, which is baby quantum group. And quotient is universal enveloping of dual quantum G hat. Yes, and because V at M is object, this is representation of G hat. So it determines the representation of Lustig quantum group. And because it is product, this is what people calling the ring object. And so it means it is something which is now, no, it is correspondence. So we have a representation of G hat, which is this, which is depending in a manifold M. And we consider it as object of a category of representation, and looking what is it. And it is a ring object of a category of representation of Lustig quantum group. So up to some details again, unfortunately, I have to stop soon, but this ring object is a function on some manifold. And it is not the real answer. So this manifold is not symplectic dual, but it is some kind of way of constructing. So no, a little bit more precisely, maybe just so what is going on? So structure is following. So next step of construction is the following. We have F, M, then we can see the vertex operator algebra V at M, then G hat is acting here. Next, it gives object of category representation of UQ of G. Q is root of unity in not in all examples, but many examples. And after that, we are looking for X with respect to baby quantum group of, for example, trivial representation with this, what is corresponding to this. It gives me some algebra which is much closer to a dual object. So yeah, so anyway, no, this is some not all, but this is part of algebraization, but what people have in mind. So if you look to the papers of, again, Finkelberg, Braverman, and Nakajima, that what they are doing, it is very close to this construction, but their approach is much more geometric. So they do not use exactly the category of representation of vertex operator algebra, but not far from that. So it is just different languages to but maybe last yes, I need to stop, I think. So excuse me. No, something on my no, I want to make just maybe the last sentence of my talk, but maybe here. So what I'm thinking about this, so I explained that from the point of vertex operator algebra, this is some duality. So for example, I have G and I have Lagrange's dual group phi. And what I explained that if we have J, L, and M, then what is here, it is the question, but from the point of view of W algebra, I just explained some machinery mechanism, how to think about it, what to put here. And after that, we can surely ask about some rather unknown things that suppose I have symplectic manifold where we have super manifold. We have the action of GL and NM. No, it is not big deal to find some kind of examples. Then I want to find the dual manifold. Yes, and the story is going on more or less by similar strategy which I explained. So I have M, then I considering the vertex operator algebra, which is corresponding to M. Then GL and M is acting here. Then I want to know about M. What is M? It is subtle things, but first I want to make up here. I want to find vertex operator algebra which pretend to be something like that, where we have, now what is possible to do is to construct such vertex operator algebra where JLN hat times JLM hat is embedding. So it is some such sort of part of duality which appear in standard things. Yes, at least it is possible, but no, this is what I'm thinking about. So how it is working and how it is really related with known things, I do not know. And I do not studied enough examples to say what is this, but at least this playing with vertex operator algebra is related with this question, but surely I skip a lot of details. But what I want to finish that there are many, many interesting questions just about vertex operator algebra, even without geometry, and they're interesting and nice. So thank you. Maybe I stop now.
Speaker.
Oh.
Yeah, let me see if there are any further questions. Okay, let me check Zoom.
Oh.
I have a question. Can you hear me?
No, I hear not very well, but I hear. Try.
Okay, I encountered such a notation as W1 plus infinity. Is it somehow related to any limit of the level in this context?
You mean what is usually such kind
Yeah,
of algebra?
yes.
No, about this, I only want to say that this is algebra is involved in this business, and it involved by the following way, that if you have W algebra just for JLN, so then this algebra is analytic continuation in N, yes? And this is more or less definitions. So you make what is this? You take universal enveloping of JLN and then make up reduction. It is something depending in N. Then the main story is that if you have just JLN, so it is possible to consider about analytic continuation in N and so on. But naively, surely we cannot do it. But if you make up reduction, then you can make analytic continuation in N, and it gives you some algebra, vertex operator algebra, and this object is just the result of such analytic continuation. And there's one more thing, that if you consider, for example, JL and M W algebra, then this algebra is the quotient of such kind W plus lambda. So what you're doing, you make up analytic continuation in N, but then you look to some other value of N, or so this algebra in principle belongs to the same family. So this algebra is the quotient of this algebra for some specific lambda. So why it is happening and what is really, it is still the same question, nothing super in this situation, but still it is correct. And I did not mention it because it is interesting. And also, it is main tool if you want to prove something about this. Because, for example, so there are several ways in principle. But if you want to see why this quotient is a W algebra of n minus 1. And the way is following. You take W infinity plus lambda, you find out by some way embedding it to JLN hat, and such that the image commute with this. This is possible to do. And after that, no, this image surely has a kernel, and factorization by the kernel coincide with this. It is strange, but the best way known for me, and maybe shortest way to prove that this cassette is really this one. Yes, maybe it does not answer to your question, but just some interesting things.
Okay, thank you.
A previous question, yes, thanks. How you can represent the of two affine algebras in terms of this W infinity plus with the unity. Okay, yes, thank you. Let me see. There are probably no further questions from our side. If anybody in Zoom, please ask. And let's thank the speaker again.
Okay. Okay, so thank you and maybe bye now. Okay.
Да, Борис Ильич, большое спасибо.
Mm-hmm.